Hi folks, welcome back to Physics with Captain Rod. I'm making this one here to help you out with number 30 in your homework. Alright, so what do we got here? We got this system here, and these two masses are tied together by ropes or something like that. And let's see, it's released from rest, and this thing hits the ground 9 seconds later. So, a pretty important thing to realize is that 9 seconds, there's got to be a substantial force, how do I want to say this, impeding the motion of this. Otherwise, this thing probably would have fallen down and hit the floor in quite a bit less time. Then the nature of that force, if we look at this, there's only two forces acting on that. There's a gravitational force down equal to mg. Then there's an upward tension. And that's it, right? Then that tension acts over here to the left on this object, right? What I'm getting at is there's got to be some sort of force hindering the motion of this object, and that's going to be occurring here. There is probably a frictional force occurring on that object. So that force is an external force to the system, and what you're going to want to do is maybe draw a free body of both objects, this one, and we'll use those here to kind of guide our work as we move things along. Now, let's see here. Part A, draw the velocity graph and find the final velocity of the system. So what you want to do is, again, you're going to do like velocity against time, and it starts from rest. So the first point at time equals 0, let's say the v is 0. Then go ahead and put another point on there. Now, I don't remember if we have the time or not. We do, 9 seconds, I guess, yeah. And then the vertical velocity is an unknown. We'll call that a v final or something like that. And then use concepts of slope and area. The area, once we get this graph done, you should have a triangular area, is equal to the distance that this thing moved, which I think is 4 meters. And from that, you should be able to calculate the v final. All right? And that's what it's asking for, the final speed of the system. All right, part B, use principles of work and energy to find the force of friction acting on the 50 kilogram mass. All right, so you write out the work energy theorem. That's the big, the big long PE1 plus KE1 plus et cetera, et cetera, et cetera. Let me add one more term to that, plus the work, the net work done on the system, equals PE2 plus KE2. Now, when we get back to my picture here, right, you always want to draw position 1 and position 2. So here's position 1. This object is here. This one is here. Position 2. Here's the 20 kilogram mass. Here's position 2. A little bit of daylight here. It's not quite hit the ground yet, because again, once it hits the ground, its velocity is 0. This object has moved to here. Now, keep in mind, the 20 kilogrammer is now moving this way. It's got a speed. This object moving this way, it has a speed. All right. So when you write out the work energy theorem, right, put a datum somewhere. I would put the datum right here, lowest point in the diagram. And what that does is this object will not have a PE2. This object will, equal to mgh. Oh, I'm sorry. Let me restate that. This won't have a PE2, but it will have a PE1 equal to mgh. My apologies about that. All right, now let's talk about the other guy. Let's talk about this. Technically, this has a PE1, mg times this height. But it also has a PE2, mg times the same height. So long story short, that's going to subtract off. I usually just advise people of this. If it's not changing in potential energy, you can ignore it. So there's no change in potential energy for this part of the system, so you don't even need to worry about it. All right. Now your KE2 term, this object has a kinetic energy of 1/2 mv squared. This object has a kinetic energy of 1/2 mv squared. All right, and you need to have both of them because we're defining our system as both of these together. Okay, under the work term. Okay, now if you have your free bodies here, let me chat about these. The free body of this object has a gravitational force down. When it moves, it is technically doing work, but that's taken into account with the PE1 term. Okay. Now let's talk about the tension. The tension on this object is up. Technically, one could argue it does work, and that work would equal tension times, I'm just going to put distance here. The distance would be the 4 meters. But the work done on this object would be negative because the force is up and the displacement is down. They're in opposite directions. All right, now when we go to our free body of this object, that tension acts to the left. The work done is going to be tension times distance, and that work term is positive. Now you'll notice that these are adding to 0 anyway if you add these up. So you don't need to worry about work terms due to the tension. Right? Right. Thinking about other forces acting on this guy, there's a vertical normal and a vertical mg. Neither of those are doing work because they make a right angle to the velocity. But there's one more. Your free body should have a frictional force at this surface. So you're going to have a work term equal to whatever you're calling the frictional force times the distance. And the distance is the 4 meters. This object is going to move 4 meters when the 20 kilogrammer moves 4 meters. And that work term is negative because the frictional force on this object is to the right, but the object's moving to the left. So yeah, it's kind of a lot of writing, but put all of that together into one work energy equation, and you should be able to get the frictional force out of that. All right, next, find the coefficient of friction between the 50 kilogram mass and the surface it's on. So frictional force is equal to coefficient of friction times the normal. So you should be getting this from part B, and this you can get from your free body. Keep in mind that the object is not accelerating up or down. So that's how you get the normal force. So that should get you through this problem. I hope you enjoyed the video. Have a great day.